All right, as we move into our next unit, we're going to start talking about chance and the chance of things happening, probability, kind of things like that. But before we can do any of that, the biggest thing that we have to do is we have to learn how to count. And what I mean by count is a lot of probability and chance is figuring out how many different ways something can occur. And so we'll have a couple different things we'll do this week on these different types of counting methods. We'll start with what's called the fundamental counting principle. So the fundamental counting principle is something you may have heard of. A fundamental counting principle says if a decision can be made, say, decision M can be made, let's say A way. So there's A choices. And decision N can be made B ways. Then the way they can be done together is A times B. That's the total number of decisions. So for example, if I want to think of something very simple, let's say I have two shirts I want to wear. I have a blue shirt and I have a red shirt. So I could choose any of those. But then let's say I have, green pants. So I have green pants and let's say black pants. So if I want to figure the number of outfits, well, I could have blue I could wear with green pants. I could wear a red shirt with green pants. Or I could wear a blue shirt with black pants, or I could wear a red shirt with black pants. So these are my four ways that could happen, but if I use the fundamental counting principle, this can happen two ways, this can happen two ways, 2 times 2 is 4. So not a very complicated theorem, not a very difficult principle to think about. You just think about how are all the different outcomes, how many different ways can something occur. So if we look at some examples here, this first one says the ice cream shop offers 3 cone sizes, 15 flavors, and 8 toppings. How many different cones can there be? So we have 3 cone sizes, 15 different flavors, and 8 toppings. So quite a few different combinations, different ways you can arrange this. So all we simply do is there are 3 cone sizes, there are 15 flavors, and 8 toppings. So all I have to do is simply multiply these out. So I get 360 different cone types. So it could be a small cone with chocolate ice cream with sprinkles, or all these different kind of ones, right? So a lot of different types of cones can be made from these choices. The second one says a Virginia license plate consists of 3 letters followed by 4 digits. How many different license plates are possible? Okay. So first of all, we have to think about how many letters there are in the alphabet. There are 26 letters in the alphabet, so that's going to be pretty important. And then there are 10 digits. There's 0, 1, 2, 3, 4, 5, 6, 7, 8, 9. So if I want to think how many different license plates there are, obviously there's a lot. Well, I have 26 choices for the first letter, and 26 choices for the second letter, 26 choices for the third, and there's only 3 letters, so those are my 3 letters. And then I have 4 digits, which is going to be 10 times 10 times 10 times 10. So assuming that nothing can be, the things can be repeated, which in most cases they can, this would be our total number of combinations. And it is a lot. If you think about 3 letters, and it could be the same letter, A, B, 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 C, 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 and then 4 digits, how many different license plates are there? There's a lot. If I take this product, I get 175760000. So that's about 17 million different license plates that could occur. So that's a lot of combinations. The more things you have, the more choices you're going to have. So here's a more relevant one. So Nick's science test had 12 true or false questions. How many ways can Nick answer these questions? So we'll assume that Nick is just going to guess. So there's 12 questions, so each time there are 2 random choices he can pick. 2, you can do true or false for each one. So for each of the 12 questions, there's going to be 2 possibilities. This way we can figure all the different ways that Nick can answer these questions. But since it's 2 times itself 12 times, it's just simply 2 to the 12th, which is 4,096. So a lot less than the license plate, but still quite a bit. Finally, this one says to enter a home, Clayton family enters a 4-digit code. How many codes are possible? So again, we'd have to make sure that numbers can be repeated and everything like that. There's no reason to think it can. So there's 10 choices for the first, 10 choices for the second, 10 choices for the third and fourth. So this would mean that 000 is a proper code, and 111 and 9110, all these would be good. So this is going to be 10 to the fourth, which is going to be 10,000. So there are 10,000 codes for this entry system, which is good because you don't want there to be too few. You don't want anyone to randomly guess what your entry code is. So the last thing we'll talk about in part 1 of these notes before we get to some of the more difficult counting principles in section 2 is factorials. Now factorials are essentially when you have some number and then you'll have an explanation point. Now all a factorial is, it's going to be the product of all the natural numbers. Natural numbers are just your normal counting numbers from A to 1. So from the biggest number to the smallest number. So for example, 9 factorial is 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. So if I do this, I just do 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. I get 362,880 as my factorial. So a really, really, really big number. So these get really big really quick. Because if you think 12 factorial is 12 times 11 times 10 times 9 times 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1. So quite a ways down. Now the way we could do that, this is going to work out to be 479,001600. So about 47 million is 12 factorial. So these get very big very, very quickly. Very quickly. So if I do 8 factorial, which is 8 times 7 times 6 times 5 times 4 times 3 times 2 times 1, I get 40,320. So if you just simply look at these two numbers, this is 9 factorial and this is 8 factorial. You can see how much bigger 9 is than 8, so this is going to increase pretty quickly. Now this one over here, 0 factorial, is one you just have to have by definition. 0 factorial is just going to be 1. So if you ever see 0 factorial, which will be something we use quite a bit, it's just 1. Now the final thing I want to look at here is what's called factorial math, where you have a couple different factorials. So in this one I have 17 factorial divided by 11 factorial. Now this is something you can certainly put in your calculator, but I want to think about it a little differently. If I think of 17 factorial, it's 17 times 16 times 15 times 14 times 13 times 12. And I should keep going all the day down to 1. But what I'm going to do is I'm going to stop here and say 11 factorial. Now why I do this, if you think of 17 all the way down to 11 factorial, this would keep going. This literally goes down to 1. But if I stop here, it gives me an added benefit. Because I have an 11 factorial on the bottom, if I stop my numbers, because I'm going down, I'm starting at the biggest one, multiplying all the way down. If I stop at a certain point, then what it does is it only lets me deal with the numbers in front, because these 11 factorials will cancel. And now if I want to do 17 factorial over 11, I just have to multiply these numbers. 17 times 16 times 15 times 14 times 13 times 12. Still a big number. This is going to be 8910720. So still a very big number, but doing the factorial math would be a lot easier than taking this and multiplying all the way down by 1 and then dividing it by all the numbers down to 1 as well. So just a little bit about the fundamental counting principle in part 1, and then our second part obviously about factorials, which we will use in our second part talking about permutations and combinations.